In this video, we're going to look at how to optimize or find the best answer to a question. A rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of its base is twice its width. Material for the base costs $10 per square meter, and materials for the sides cost $6 per square meter. We want to find the cost of the materials for the cheapest such container. So we need a rectangular box. I'm going to draw a diagram here. And there we go. So our box, the base has a length and a width, and then there's the height. In the text, it says that the length of the base is twice the width. So here's the length of the base, or the face that the box is sitting on, and I'm going to call that 2W. So now I'm only going to have 3 variables because I don't need to use L anymore. Okay, every optimization problem is going to have a constraint. And the constraint in this problem is that the volume of my box needs to equal 10 cubic meters. Volume is length times width times height. But since I know that the length is 2W, I'm going to make that substitution here. So my volume equation is going to be 2W squared times the height. I'm trying to optimize cost. So now I need to make a cost equation. Oh, you know what? Let me go back to my volume equation here. My volume needs to equal 10. Okay? So this is my constraint. My constraint is that 2W squared H must equal 10, and I can even simplify that by dividing by 2. W squared H must equal 5. Okay, now I'm going to set up the equation that I'm going to optimize, which is the cost for the materials to build this box. So I'll call C my cost function. The cost is going to equal $10 per square meter for the base. Well, the area of my base is 2W times W, and then that has to be times 10. Okay? So this right here is my base. Okay, then $6 per square meter for the 4 sides of the box. Remember, this is an open top, so I don't have a top. There's only going to be 5 sides, the bottom and the 4 sides going around. So the sides in the front and the back here, and the side in the back that we can't really see, the area of those faces are 2W times height, and there are 2 of them. So there are 2W times height, and the cost of those faces is $6 per square meter. And then I've got the left and right sides of my box over here, and there are also 2 of those, the left side and the right side. They each have an area of W times H. So that's 2 sides, W times H, at $6 per square meter per side. Okay, let's simplify this equation here. I have C equals 20W squared plus 24WH plus 12WH. And, oops, I should say this side is the left and the right. Okay. And then you can see that I can combine some like terms here. I have a 24WH and I have a 12WH. Let's combine those into 36WH. Okay, now at this point I need to make a substitution so that I only have one variable in my equation. Right now I have cost in terms of W and H. So this is where I use the constraint. I look and I can see in my constraint I can easily solve for H. So I have H is going to equal, I'm going to use this one, 5 over W squared. Okay, so I'm actually taking my simplified version, and I get this substitution. H is 5 over W squared, and I'm going to plug that into my cost equation, and then I will only have one variable. I will only have W's in my cost equation. So I have cost in terms of W is 20W squared plus 36W times 5 over W squared, which is 20W squared. 36 times 5 is 180. And then I'm going to have W to the negative 1. So I am all ready to take the derivative now. The derivative of my cost equation, or C prime of W, is 40W to the first. This is going to be minus 180W to the negative 2. And I'm going to rewrite this 40W minus 100 over W squared. And then I'm going to give everything a common denominator. So I need to multiply my 40W by W squared over W squared so that everything has a denominator of W squared. And when I rewrite that, I'm going to have my derivative equals 40W cubed minus 180 over W squared. Great. So now I need to use the derivative to find the critical points of my function. Critical points will give me possible minima or maxima. Of course, I'm looking for a minimum because we want to minimize the cost of building this container. From the bottom, I get W equals 0. When W equals 0, my cost derivative is undefined, so that's a critical value of the cost function. However, W can't equal 0. In the context of this problem, if W is 0, we won't have a base. So W is not in the domain of this problem. So now I'm going to look at the numerator. What makes my derivative equal 0? So I get 40W cubed equals 180, or W cubed equals 9 over 2 when I divide by 40 and then simplify the equation. And that gives me W is the cube root of 9/2. Okay. So I have another critical value. W is the cube root of 9/2. But now I want to confirm what kind of a critical point is that for this function. So I'm going to make a sign chart. I'm going to make a sign chart for my derivative. I'm going to start my sign chart at 0 since, again, W values less than 0 aren't applicable for my box. And then my one critical value here is the cube root of 9/2. And this is a sign chart for the derivative of my cost equation. So, okay, so I'm going to get my calculator out here, and the cube root 9/2 to the 1/3, oh, let me put that in parentheses, 1/3, the cube root of 9/2 is about 1.65. So I know that 1 is in this interval. If I plug a 1 into my derivative equation, I get 40 minus 180 over 1, which is a negative number. If I plug a number from this interval into my equation, I get, let's say I plug a million in, I get 40 times a million cubed minus 180 over a million squared. Well, that is certainly a positive number. So I've just confirmed that C of W has a minimum when W is the cube root of 9/2, and I know this because C prime of W changes from negative to positive at W equals the cube root of 9/2. And we know that when a derivative changes from negative to positive, the function is changing from decreasing to increasing, and therefore the function has a minimum value. All right, so let's go back and remind ourselves, what is the question asking? And the question is asking to find the actual cost, the minimum cost of this box. So I'm going to take my W is the cube root of 9/2, and I'm going to plug it into the cost equation. Remember, here I have the cost equation just in terms of W. So it is going to be C, the cost when W is the cube root of 9/2, equals, and I am using this equation right here. Here's my cost equation. That's going to be 20, the cube root of 9/2 squared, plus 180 times the cube root of 9/2 to the negative 1. So let's see what I get. So in the calculator, remember, you never want to use a rounded number. You always want to use an exact value or a stored value when calculating answers. So I'm just going to store that as x. I have the cube root of 9/2 stored as x. So I'm going to have 20 x squared plus 180 x to the negative 1. And I get 163.5408. But since we're talking about money, I'm going to logically round to dollars and cents. So my answer is $163.54. $163.54. This came from 163.54085 and so on. But since we're talking about money, we round to dollars and cents. So again, let's review what we did here. When you have an optimization problem, you want to figure out what is the constraint in your problem. Our constraint was that the volume of our box had to equal 10 cubic meters. Then you write an equation for what you're trying to optimize. I was trying to optimize cost. So this is my cost equation. In order to take the derivative, you need to simplify your equation by eliminating a variable using your constraint. So I eliminated h using the constraint equation. I took the derivative to find the critical values, found the critical value that represented a minimum for the function, and then went back and answered the question being asked, which is, what is the minimum cost?